Hello and welcome back to this channel. Dear students, today's topic is logic gates and De Morgan's theorem. For every topic, I will be telling you the questions that can be asked in the exam. So three questions can be expected from this topic. First is, I'm just talking about logic gates. For De Morgan's theorem, I will provide another question set. So draw symbol and truth table of AND gate and OR gate. Second question can be explain how XOR gate can be used as an inverter, means how it can be used as a NOT gate, or draw two input XOR gate and implement it using basic logic gates. First we will talk about the logic gates. You will get answer of all these three questions. So there are three basic logic gates. One is known as NOT gate, second is AND gate, and third is OR gate. These are the basic logic gates. Using these basic logic gates, another gates can be implemented. So let us discuss each gate in detail. Now, as I mentioned, there are three basic logic gates. One is NOT, second is AND gate, third is OR gate. You just have to remember the symbols, which are again pretty simple, and some smaller equations. You will be in a position to generate any truth table. You rather don't have to mug up this truth table, rather you can't, because there are many truth tables. So I will tell you simple tricks how to remember these truth tables. First is the NOT gate. As the name indicates, it is not operation, means it performs reverse of operation. So it changes input to the opposite logical level. So do remember this symbol. This bubble stands for inverting. So if applied input is A, output is A complement. This A bar is also known as A complement. Complement means opposite. So very simple. If input is, this is the truth table of NOT gate. If input is 0, output will be 1 because it performs opposite operation. If input is 1, output will be 0. So this is the NOT gate. Second is AND gate. You have to remember this symbol. This is the symbol of AND gate. I have shown two input terminals. There can be 3, 4 input terminals. Output is given by the equation A into B. Now, listen carefully. Even if you know this equation A into B, you can well generate the truth table, or remember the sentence like this. For AND gate, output is high when all inputs are high. There are two inputs as I shown in this diagram. When all inputs are high, then only output is high. Now, I have considered two inputs, so there are 4 possible combinations. I hope you might be knowing these possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. These are the 4 possible combinations. So, if you are remembering this equation, A into B, very simple: 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. Or do remember this sentence: output is high when all inputs are high. There are two inputs. All input means when both the inputs are high, as in the in case of the last session, it is 1, 1. So both inputs are high, so output is high, otherwise output is 0. So this is the case for AND gate. Third is known as OR gate. This is the symbol of OR gate. Equation is Y stands for output is A plus B. Now do remember, this is not mathematical addition. In mathematical addition, we perform the addition like this: 1 plus 1 is equals to 2. In binary systems, actually addition is 1 plus 1 is 0 and carry 1. But just to make the thing simple, this equation is A plus B. This is binary addition. Or remember this sentence for OR gate: output is high when at least one input is high. Do remember this word, at least. At least when one input is high, then output is high. If both inputs are high, then also output is high, because the wording is at least one. Or remember this equation: A plus B. For example, both inputs are, again I have written the same combination: 0, 0, 0, 1, 1, 0, 1, 1. A and B are two inputs. So A plus B, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is actually, it is 0 and carry 1. But just to make the thing simple, remember it like this: 1 plus 1 is 1. So this is the operation or truth table of the OR gate. If you are following this statement, output is high when at least one input is high. Look at the inputs. Here there are two inputs, out of which one is high, so output is high. Again, this one input A is high, so output is high. Here both the inputs are high. The wording is at least one. Since both are high, output is high, like this. So this is the case for basic logic gates, which are NOT gate, NOT gate, AND gate, and OR gate. Next is universal gates. These gates are NAND gate, N-A-N-T, and NOR gate, N-O-R. These are known as universal gates because by using these gates we can implement any basic gate like NOT gate, AND gate, and OR gate. So these are known as universal gate because we can implement the basic gates by using those gates. So these are not AND gate, that is NAND gate. N stands for not. Not means reverse operation. Second is NOR gate, not OR gate. Now we have already studied this AND gate and OR gate. If I want to implement NAND gate, then this is the diagram, this is the symbol which we already discussed. This N means negative operation, just draw one bubble. This is the symbol of NAND gate. If you know AND gate, just draw one bubble. This is symbol of NAND gate. And when you are inverting it, in case of final equation, this was the original equation for AND gate, draw a complement or draw a bar. So equation is A into B bar. This is the equation of output for NAND gate. It is not AND. Operation is pretty simple. We have already discussed this truth table for AND gate. It is inversion. Output is inversion or negative of the output of the AND gate. So this is the output of AND gate which we have already discussed. Just change these levels. This is 0, 0, 0, 1. It will be reverse. So it will be 1, 1, 1, 0. This is the truth table of NAND gate. Very simple. If you know AND gate, you can well generate NAND gate within a minute. Next is NOR gate. Again, this is the symbol of OR gate. It is NOR gate, that is negative OR gate or complement OR gate. So again, draw one bubble. This is the symbol of NOR gate. The equation of the OR gate is, output equation of OR gate is A plus B. Since we have drawn a bubble, so we need to draw the complement, that is A plus B bar. This was the original truth table which we had discussed while implementing the OR gate. Now it is A plus B bar or it is a NOR gate. So just invert the outputs. Input remains as it is. Just change the outputs, invert the outputs. This was earlier 0, it becomes 1, and whatever ones we had written earlier, it becomes 0. This is the truth table for NOR gate. Next part is exclusive gates. There are two types of exclusive gates. One is XOR gate, second is XNOR gate. We already studied OR gate and NOR gate. So the basic symbol of OR gate is like this. This is the basic symbol of OR gate. This is exclusive OR gate. So draw one added symbol like this. So this represents exclusive OR gate. The output is given by this mathematical notation. It is read like this: A XOR B. I mean, I have drawn one circle and marked positive sign inside the circle. It is read as A XOR B. So output is combination of exclusive addition of A and B. It is known as XOR. Now do remember this sentence for XOR logic gate. Output is high when there are odd number of ones in the input. This part is important. I have drawn the truth table. This truth table I have generated for 2 inputs. It can be well written for 3 inputs. Do remember this basic. When there are odd number of ones, output is high. Otherwise, output is low. So look at the first combination. I have considered 2 inputs. 0, 0. There is no 1. So output is 0. 0, 1. It is the number of ones is 1. Only 1 times logic 1 is there. So 1 is an odd number. So output is 1. Then 1, 0. Again, only 1 times logic 1 is there. So output is 1. That is high. Then 1, 1. Both the inputs, that is both A and B, are logic high. So there are 2 number of ones. 2 is even number. So output is 0. Likewise. So this same table you can well draw it for 3 number of inputs. For example, if you are writing the table for 3 inputs and combination is 1, 0, 1. So these are the 3 inputs. Just observe this. There are 2 number of inputs, 2 number of ones. So 2 is an even number. So output will be 0. If you come across 1, 1, 1. There are 3 number of ones. Since 3 is an odd number, output will be 1, and so on. Next is XNOR gate, that is exclusive NOR gate. We have studied the NOR gate. Basic symbol of NOR gate is like this. it is not OR. So this is the basic symbol. What we have done, I have just added this one extra symbol. It becomes XNOR gate. Now for XNOR gate, the output is represented by the symbol A, then draw a circle and mark dot inside the circle. In case of XOR gate, I have marked plus sign inside the circle. This is XNOR gate, draw a dot inside the circle and B. So it is read like this, A XNOR B, A XNOR B. Now do remember this sentence for XNOR gate. Output is high when all inputs are same. If you are talking about two inputs, I have drawn the truth table over here. Then the statement is when output is high when all inputs are same. There are two inputs. So whenever both the inputs are same, then only output is high. For example, first combination 0 0. There are two inputs and both are same. It can be 0 or it can be 1. Both are same. So output is 1. 0 1 1 0. Two inputs are different. Output is 0. Then last combination 1 1. Both inputs are same. That is logic 1. So output is 1 and so on. So these two gates, that is XOR and XNOR, are known as exclusive gates. The next part is how to design the basic gates. Basic gates are NOT gate, AND gate and OR gate. How to design basic gates using universal gates. Universal gates are NAND gate and NOR gate. The question is, using universal gates, draw NOT, AND and OR gate. So this question is expected for 3 marks. If you just remember one screen, you will be in a position to design any basic gates using the universal gates, that is using NAND gate and NOR gate. Now how to remember it? This first column, this part represents the designing of NOT and OR gates using NAND gate. Second part indicates the designing of same, that is NOT gate, AND gate and OR gate using NOR gate. Now first part. First, if I want to draw a NOT gate using NAND gate, how to do it? We know that if I am talking about an AND gate, the symbol is like this. Output of AND gate is given as A dot B. If it is a NAND gate, I will have to draw a bubble and output is the complement of this, that is A dot B bar. Same way, make it simple. If you want to obtain a NOT gate is basically performing inversion operation. That means if you apply logic 0 at the input, output will be 1. And reverse way, if you apply logic 1 at the input, output will be 0. So how to do it? If you are using a NAND gate, very simple trick, just combine both the inputs. So I have combined both the inputs, A and B, and apply it to the NAND gate. Output will be A dot B bar, which is the output of NOT gate. This is the design of NOT gate using NAND gate. Same way, if you are using a NOR gate, then like the previous case, just combine both the inputs, use the NOR gate. Output, in case of one more thing, in case of OR gate, output is given as A plus B. If I will draw bubble, then it is NOR gate. So in that case, the output is complement. So Y is A plus B bar. Second, you want to draw AND gate using NAND gate. Now do remember this diagram. Again, it is not at all complicated. It is pretty simple. I am using two NAND gates. I am using two NAND gates. First NAND gate is a normal NAND gate like the previous one, whose output is given as A dot B bar, which we have already discussed. Second NAND gate, this same diagram I have used. That means this second NAND gate is acting as a NOT gate. So output of first NAND gate, which is the standard output, A dot B bar, is applied to the second NAND gate, which is acting as a NOT gate. So since it is a NOT gate, I have drawn one more complement. So it becomes double complement, double bar. Whenever double bar is there, it gets cancelled. So output is A dot B. This is actual output of the AND gate. So this is the way how to perform, how to draw AND gate using NAND gate. Second, using NOR gate. If you want to design AND gate using NOR gate, do remember this diagram. Two inputs I am using, A and B. So there are two NOR gates I have used. This is the same diagram as the generation of NOT gate using NOR gate. Same diagram I have drawn over here as well as over here. So two inputs are there, A and B. These two things are acting as a NOT gate. So output will be A bar and B bar. For the third NOR gate, it is the normal NOR gate. We know that in case of a normal NOR gate, the output will be, again, it is written like this. These are the two inputs, A bar plus B bar, and again bar. because it is a NOR gate. So output becomes A dot B. Now how come this is A dot B? Why this plus sign is changed into multiplication sign? This will learn while studying the De Morgan's theorem. Presently just remember, this is the output of, we are generating a AND gate, so output should be A dot B. That's what we are generating using this diagram. I will explain you while studying this De Morgan's theorem. Third, OR gate. How to generate OR gate using NAND gate? Very simple. Just from the exam point of view, how to memorize the things. It's not technical. How to memorize the thing. Similar type of diagram I have drawn it over here, but it is designing using NAND gate. So instead of NOR, I have used NAND gate. These first two NAND gates are acting as a NOT gate. So output is A bar, B bar. Second is normal NAND gate. So I am taking bar. So it is A bar dot B bar and one more complement. So it becomes A plus B. Again, I will explain it while studying this De Morgan's theorem. So just remember, it is a OR gate. So output must be A plus B. Second, again, just for remembering the things, similar type of diagram I have drawn it over here. This is the generation of OR gate using NOR gate. This second diagram I have drawn it as it is, but it is using NOR gate. So first is NOR gate. The normal output is A plus B bar. Second NOR gate is acting as a NOT gate. NOT gate means just take complement of this part. So double complement is there. So whenever double complement is there, the bar or complement gets cancelled. Output is A, B. Here there is, here there is no double complement. This is individual complement and then common complement. It is different case than this. In this case, the plus sign becomes equals to sign. Here, plus sign remains as it is. So, if you just remember these diagrams, you can well generate any basic gate using the universal gates. Next, the most important part is De Morgan's theorem. The question is very much straightforward. State and prove De Morgan's theorem. There are two theorems. Theorem 1. We'll discuss this statement later. First, I will explain you what this theorem is. If you are performing A plus B complement, this bar indicates complement, then answer is A bar dot B bar. That means, if you are taking addition of two inputs A and B and you are taking complement of it, that is equals to complement of A bar into, it becomes multiplication, complement of B bar. Make the thing simple. How to remember this sentence? How to remember this statement? If you break the line, change the sign. This is the original line. This bar indicates the line. If you are breaking the line, you are writing it separately for each input. Then if you are breaking the line and if you are writing it separately, change the sign. So this plus sign becomes into sign. Very simple. It is applicable for any number of inputs. I have just written it for two inputs A and B. It is applicable for any number of inputs. If you are breaking the line, the sign gets changed from plus to minus, plus to multiplication, sorry. Now, how to prove it mathematically? Consider LHS part. LHS part is A plus B complement. It is A plus B. That means I have to use a OR gate and it is complement. So I have drawn one NOR gate. So output of NOR gate indicates A plus B bar. This is the standard equation of output of a NOR gate. A plus B bar. At the RHS, I have A bar into B bar. The dot sign multiplication indicates we have to use an AND gate, but it is A bar plus B bar. That means initially we have to take complement of both the inputs. So I have written AB. I want to generate A bar. So take complement means just draw bubble. So at the input side I have drawn bubbles. So it becomes A bar. Second becomes B bar. It is an AND gate. So output is A bar dot B bar. How to prove it? This is the truth table which proves LHS and RHS. Now, as far as LHS is concerned, I have written two inputs, normal sequence 0, 0, 0, 1, 1, 0, 1, 1. A plus B. This is the output of OR gate. So we know standard output of OR gate which we have already discussed. And second is A plus B bar. This is the equation of LHS, A plus B bar. Now, in this case, since it is bar, we have to just write the complement of this. So, I have written the answer A plus B, which is the output of OR gate. Complement of this is the 0 becomes 1, 1 becomes 0, 0, 0. This is the actual output. Look at the RHS. It is A bar dot B bar. That means I have to take multiplication. So, it is A bar, B bar. So, these are the two original inputs A, B. just take the, to generate A bar and B bar, just take complements of this. This is 0 0, complement of this is 1 1. This is 0 1, complement of 0 is 1, complement of 1 is 0. Likewise, I have written inputs. Now simple, A bar into B bar, 1 into 1 1, 1 into 0 0, 0 into 1 0, 0 into 0 0. So since both these outputs are same, this is the verification or proof of De Morgan's theorem 1. What the statement indicates? Complement of product of variables. Now don't do it like a normal cases. Consider RHS first. So RHS is this A bar dot B bar. What do we have written? Complement of product of variables. You are taking product of this complement A bar dot B bar is equal to addition of complement of variable. Take addition and then complement of variable. So this is the theorem 1. Now let us prove the second theorem, that is the last theorem of De Morgan's theorem. Now the last part of this session is proof of theorem 2 of De Morgan's theorem. Statement is similar to that of theorem 1, only the wording is changed. How to remember this sentence? This was a complement of product in the initial statement. It becomes addition, and here I had written it is equals to addition. So you just have to replace addition by product. That's it. Now this is the logical expression that is more important. What I said, how to remember it? If you are breaking the line, change the sign. Actually, it is A into B. So I will try mark here dot A into B bar. If you are breaking this line, it becomes individual. So this into sign is changed to plus sign. This is the way, simple way to remember this statement. Now consider LHS part. It is A into B complement. It is the standard equation of NAND gate. So I have drawn this NAND gate to represent the LHS side. At the RHS, we have plus sign. Plus sign is applicable for OR gate, but it is A bar plus B bar. So first take complement of two inputs A and B. Complement means drop bubbles at the input side. So this represents A bar. Second bubble represents B bar. And then it is applied to OR gate. So this is known as bubbled OR gate. So output is A bar plus B bar. Now the truth table, rather proof. I have drawn LHS truth table for LHS side first. So two inputs are there, A, B, standard combination 0 0 0 1 1 0 1 1. For next column, third column, A into B, simple way, 0 into 0 0, 0 into 1 0, 1 into 0 0, 1 into 1 1. This is the third column. Then A, B bar, that means complement of this output. Complement of this means 0's complement is 1, then for 0 again 1, for 0 it is 1, and for 1 its complement is 0. So this is the last column, that is output of LHS side. So this is the LHS side whose output I have generated in the truth table. Then consider RHS side. At the RHS, I want to generate this equation A bar plus B bar. So I have written values for A bar and B bar. How I have written it? Very simple. It is 0 for for A bar it becomes 1. Second input for B it is 0. For B bar it is 1. Likewise. So I have written A bar and B bar in these two columns. Then A bar plus B bar. Simply take addition. 1 plus 1 is 1. Then actually it is, I have told you earlier, it is 0 and carries 1. Just to remember it like this. 1 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. Since these two outputs are same, we can say De Morgan's theorem is verified. So dear students, that's it for today's session. Thanks for attending this video. Thank you very much.